Welcome. Let me say something about the relation between geometry and probability theory. There are strong links between these two areas. I was teaching differential geometry last semester and probability theory this semester, so it's kind of nice to combine these two things. Mathematically, there are very strong links. In physics, we don't really know because Riemannian geometry is related with general relativity and probability theory is more related with the quantum world. But integral geometry is a nice link between these two areas. So essentially anything you're looking at in geometry, like length, volume, area, curvatures, they can be understood integral geometrically. And it's much more elegant than the classical tensor calculus framework, which breaks down if the manifold has singularities, like you have cusp or things. So you have to work harder in that case. Integral geometry doesn't care about this. You just look at expectations of random variables, and if the probability space is nice, then you have no problem. And the one advantage is that in probability theory you can change your sigma algebra, you can change your measure, and so these deformations are possible, like in Riemannian geometry where you can change the metric. So let's look at, so this week I was looking at some experiments, and that prompted me to talk about this. When you look at indices, Poincaré-Hopf indices, which are divisors on a manifold, which add up to Euler characteristics, then you can take the expectation of this if you have a probability space of functions, and then you get curvatures. And so you can also look at, instead only on looking at the expectation, which gives you the curvature, you can also look at correlations, or the variance even at the point. What is the variance of that random variable at some point, or what is the covariance, or what is the correlation between two different points? And it's interesting because it's not decorrelated. Even if the points are far away, there's no kind of causality kind of from a physics point of view between the 2 points. There are correlations, and the reason is that the indices add up to Euler characteristics. So there is if you know that the index here is 1, then the index has to be 0 here automatically, because the sum is 1 for this network. So you can do that on any network, and Poincaré-Hopf works for any network, also Gauss-Bonnet works for any network. And there is a natural, theory in differential geometry, which is kind of a famous theorem, Gauss-Bonnet theorem, which gives you the Euler characteristic in terms of curvature. And this theorem is kind of if you look at it from the integral geometric point of view, the theories are almost identical, right? So here you have indices, here you have indices, Poincaré-Hopf indices, which are integer valued points located on the critical points of a Morse function, either 1 or -1, or at Morse. For a Morse function, it's just 1 or -1. But in general, you can just take integer values. So I'm fascinated by this because I also was looking at this formula. There's a formula in the case of manifolds which kind of sees the index as an expectation of, or sees the index in terms of the Euler characteristic of a level set in the unit sphere. The unit sphere is q-1 dimensional for a manifold. You take a random submanifold, which is q-2 dimensional, and you look at the Euler characteristic, you look at the expectation of this, then you get the curvature, which is very nice because when you look at it in odd dimensions, it's automatically 0, because Q minus 2-dimensional manifold in an odd-dimensional manifold is odd-dimensional and has 0 Euler characteristics. So you kind of see, so in odd dimension there is no 1 here, related to the fact that the unit sphere has Euler characteristic depending on the dimension. So this is just for even-dimensional manifolds. Here you have a very strong link between the discrete and continuum, and it's this fact that it's an expectation of an integer valued function which makes it nice, right? If you have a network or you have a manifold and you have an index here which is 1, right, and both in the discrete and in the continuum the index is equal to 1, maybe it's a maximum or, you know, for maximum or minimum, then you have this integers, and integers correspond completely between the continuum and the discrete. Then if you take expectations, you get real numbers. But it's much harder to make the link on the level of curvature. So that's why this integral geometry is so nice. Another example is Crofton, which is a very classical theory. It may be the oldest theory where geometry and probability theory are linked. It's a Buffon needle problem, right? That you can compute lengths of curves you can see as an expectation of the number of roots you have of a random function on the manifold. And also this kind of becomes natural. If you take a general Riemannian manifold, you can isometrically embed it in somewhat Euclidean space or projective. I like more the projective spaces because then there is a natural measure of functions, Haar measure, right, of functions, and then you can this is more elegant. But what happens with often with the Crofton formula is you take a curve and you look at the expectation value of how many times does a random function here have a root on that curve. Of course, that's proportional to length, and so you have just a constant here. If the measure is rotationally symmetric, it has to be the Euclidean measure or the rotational invariant measure on the projective space. It has to be the usual length, and then because it's isometrically embedded, it's also the length on the manifold, on the Riemannian manifold. So there's a very natural link here, and the same thing works also in the discrete. You can, with probability spaces of functions, you can measure lengths, or you can measure areas, or you can measure volumes. You can measure any k-dimensional property. And there's a Hadwiger theorem in the continuum which says, classifies all the invariants which are invariant under rotations and translations, and so they are just in any dimension there is just an invariant, and that works also here. So in this case, the number of vertices, the number of triangles, the number of tetrahedra, etc. These are valuations. Also the Euler characteristic is a valuation. But the probability space can be changed, so you can modify the probability space, you can deform the probability space, which produces you a modified distance. So you can somehow also here, by just changing the probability space, you can get different Riemannian metrics, or metrics which are not even Riemannian. So it's not always, if you take that, in general that's not yet the metric, but then you can take the Kolmogorov quotient and quotient out all the points which have zero distance, and then you get the metric space. It's not more a manifold in general then, depending on your probability space. But if the probability space is nice and comes from a nice embedding in a Euclidean space, and you look at the nice Haar invariant measure, so then you have the usual theory, and that's the link between differential geometry and probability theory. That's it for today.